Today we'll cover an important topic that TIG welders definitely need to know: stainless steel welding. Stainless steel TIG welding is more than just laying a bead. Heat, cleanliness, gas shielding, and tungsten choice are like links in a chain. If even one of these links is wrong, the result will never be high quality. First, the welding machine must be set to direct current electrode negative. This way, about 75% of the heat goes to the workpiece and the tungsten stays cooler. Penetration is more controlled and the bead comes out narrower and cleaner. Stainless steel cannot be welded with alternating current. Alternating current is for aluminum. Using alternating current on stainless steel ruins the job from the start. The amperage setting should be based on the material thickness. As a general rule of thumb for stainless TIG welding, use about 75 to 100 amps for every 1/8 inch of material thickness. For example, 75 to 100 amps for 1/8 inch stainless and 140 to 180 amps for 3/16 inch is ideal. For those using the metric system, the equivalent rule is about 30 to 40 amps for every millimeter of material thickness. Commonly used tungstens in stainless steel TIG welding are red, yellow, blue, purple, and gray. When working with thin materials and low amperage, gray tungsten provides a more stable, soft, and controlled arc. This reduces the risk of burn-through and spreads the heat more evenly. White and green tungstens are generally not preferred for stainless steel welding. These tungstens are more suitable for alternating current aluminum welding. It's common to use 1/16 inch diameter tungsten for thin materials and 3/32 inch for thicker ones. However, choosing the right tungsten isn't enough on its own. How the tungsten is sharpened directly affects the weld quality. For stainless steel, the tungsten tip should be sharp and ground lengthwise at an angle of about 15 to 30 degrees. This focuses the arc better, results in a narrower bead, and increases heat control. Incorrect sharpening equals an uncontrolled arc. 100% pure argon should be used in stainless steel TIG welding. The gas flow rate should be 20 to 30 cubic feet per hour, which is about 10 to 15 liters per minute. More gas doesn't always mean better shielding. Excessive gas creates turbulence and can pull air into the shielding area, causing the weld bead to deteriorate. For thick materials, using an argon-helium mixture increases heat input and deepens penetration. This allows for faster and more controlled progress. The post-flow gas time after the weld is finished is extremely critical. Since the weld and tungsten are still hot, gas shielding must continue for a few more seconds. If the post-flow gas is cut early, the tungsten tip oxidizes and discoloration occurs on the weld surface. This leads to a decrease in the quality of the weld. In stainless steel TIG welding, 5 to 10 seconds of post-flow gas is sufficient for most applications. Using a gas lens for more stable gas shielding provides a great advantage, especially in stainless steel. The filler wire must be compatible with the base material. For example, if you're welding 304 and 304L stainless steel, use ER308L filler wire. For 316 and 316L, use ER316L filler wire. Welding wires should be stored in a dry environment, kept free of moisture, and handled as little as possible. Damp wire causes porosity. During application, the travel angle and wire feeding technique are also of critical importance. The torch is generally held at a 10 to 15 degree push angle. The filler wire should be fed into the weld pool rhythmically and in a controlled manner within the gas shield. If the wire goes outside the gas shield, it oxidizes, and this oxide is carried into the pool. This situation causes porosity and a weak weld. Therefore, filler wire should be fed by pushing, not pulling, and the wire tip must always stay inside the gas shield. Stainless steel is not forgiving of dirt. Cleaning with acetone before welding and using a wire brush specific to stainless steel is essential. Wire brushes and stones used on carbon steel contaminate stainless steel and cause rusting later on. If you see rust after welding, the reason is 90% contamination. Stainless steel retains heat. That's why the arc distance is kept short. The torch is advanced in a steady manner. The amperage is constantly adjusted with the foot pedal. Additionally, using pulsed current is very effective for keeping the heat input under control. Thanks to pulsed current, heat buildup is reduced and the weld becomes narrower and more controlled. In thin materials, the risk of burn-through decreases and distortion is minimized. When there is excessive heat, blue-purple discoloration and distortion occur. This means that the corrosion resistance has decreased. Remember, a weld that looks good but is overheated is a weak weld. In summary, when you use the right settings in stainless steel TIG welding, you get top-level results in terms of both appearance and durability. If you think this video was helpful, don't forget to like it and subscribe to the channel for more TIG welding tutorials. See you in our next video.